Thanks to the chair for the introduction, and many thanks to the organizers who gave me the opportunity of speaking to you of a subject of the future. I mean carbon dioxide utilization. So in my work, I will not speak about how to minimize the production of CO2, but how to minimize the emission of CO2 to the atmosphere by converting CO2 into useful products. This is CCU technology, which has been mentioned yesterday, and it has been the leitmotif of my research during all my scientific life, which went through different stages in Italy and abroad. And at the end, I also founded a company, a startup with Professor Di Benedetto on carbon recycling. At the moment, I am a member of several panels and boards all around the world, which work on preparation of reports on how to use carbon dioxide, which are the conditions for CCU. So we have heard these days about strategies for avoiding atmospheric CO2 that are based on the reduction of CO2 emissions. So you know everything about that. I will go to the lower part of the slide, to the blue part, the CO2 capture, CCS versus CCU, and the use of perennial and renewable energies in combination with fossil carbon in order to reduce the CO2 in the atmosphere. So all this is relevant to climate change. So how to deal with climate change, trying to get stable situations. So as it has been mentioned, this is a very important point. The main issue with CO2 utilization is the energy issue. So CO2 lies at the bottom, you see down there, of the energy, because it is the end product with water of all combustion processes. So it has no energy in it at the end. So it can be used for the synthesis of some chemicals with very little energy input, and this is the carbonates. Indeed, if you convert CO2 into calcium carbonate, you still gain energy because carbonates are still lower in that diagram. But if you want to go to energy-rich products like methanol, like methane, so energy for getting back energy from CO2, then you have to push a lot of energy in that. So the question is how to get this energy. So this diagram is separated into two parts. The upper part is the chemistry of CO2. The lower part is the energy dealing with CO2. If you want to make chemicals, you can do that with very little energy. And this is possible in a fossil fuel-dominated energy situation. But if you want to convert CO2 into energy products, the lower part, the red part, then you need an input of energy. And you cannot do that with fossil fuels, because otherwise you will produce more CO2 than you convert. So you need at that point a combination with other energy sources, perennial energy sources, and hydrogen also. So you can use solar energy, you can use wind energy, you can use geo-hydro energy for providing hydrogen, which is needed for the CO2 conversion. This is a key point. If you want to convert CO2 into methane, into methanol, you need hydrogen. And this hydrogen cannot be fossil hydrogen, must be hydrogen which comes from water, possibly not drinking water, but industrial water. So that's not an easy approach. You need an integration of technology. So the lower part is the future, and we need really innovative technologies to get there. We still have part of them in our hands, so that's really a visionary area in which we need to develop a lot of our knowledge in order to reach some results and benefits. So this table, you know it very well, gives on the first column the ratio between the resources and the production. So you see that coal is by far the source of energy that has a longer life. And the other columns gives you the situation in different parts of the world. So you see that it is quite different. So the ratio, the resource production, the average over the world is 153, but if you go to European countries, it is 360. So it can be much different between the areas of the world. So that's very important to know. So if you want to use CO2, the first thing you have to do is to capture CO2. Where can you get CO2? So you have here plenty of sources. The power stations include also the integrated gasification IGCC, which can give very interesting CO2, quite pure. But the problem with these sources is that they have different concentrations and they have different purities. So you need technologies for CO2 recovery. That means to spend energy. Where to get this energy? If you use fossil fuel for getting this energy, you are just expanding the utilization of CO2 and you are reducing the ratio resource to production. So that's a key point to which we have to give an answer very soon if you want to use CO2. So if we exclude power stations, we have at our hand today 3.5 gigaton per year of CO2, which have a good purity and can be immediately used. So I refer, for example, to the fermentation processes, 95% plus purity of CO2, completely different from power station. So we must use our brain. We must be clever and make the right choices at the right moment. We can capture CO2 from the atmosphere, but we have to spend a lot of energy because we have to concentrate CO2 from 400 ppm, which is the level in the atmosphere, to pure streams for utilization in the chemical or energy industry. And this means a lot of energy. We cannot use fossil energy for doing that. We have to rely on perennial and renewable energies. So if we compare now CCS and CCU, this has been already discussed yesterday, for example, they are quite different views. In CCS, we have a linear economy, and at the end of this, we take CO2 out and we store underground, or in the ocean, or whatever you want. In the CCU, we go in a circle. We use carbon dioxide, we use external, non-fossil carbon energy sources for its conversion into energy or a chemical. We use the chemical, we use the energy source, and then we produce again CO2, which must be cycled. So these are two quite different views about our future. The cyclic economy is real, the future for us, but we need investment. If yesterday was said that the investment in CCS is low, has been low so far, $20 billion in the last 20 years, in CCU we are at the level of a few hundred millions. So they are not comparable. And today there is a lot of interest in pushing on CCU because CCU means saving carbon, saving fossil carbon. Where are we with the CO2 utilization? Today, we use 200 million tons per year of carbon dioxide in chemical industry. So it's much, much, much more than is stored underground, which is at the level of 5 to 10 million tons per year, much, much more. Still, the impact on climate is very low because the emission is very high. In the short term, the forecast is that 5 years from now, that we can grow from 0.2 to 0.3 gigaton per year. Per se, a huge jump, but if we compare with the 35,000 million tons per year, it's still very low. In the medium term, we can go to the gigaton, which is more significant, and in the long term, we can go to 10 gigaton. That may be 1/4 of the future, 1/5 of the future emissions. That has an impact on climate. So as you see, is a very long-term perspective that we have to manage with the knowledge of today. So this is very difficult. It's not very simple. This has been said this morning. We need invention for new inventions for getting there. And that's why excuse me. Okay. That's why I think that CCU is really something that must catch the attention of young people. They are the future. CCU is the future. Which are the effects of CCU utilization? They are listed in this slide. We can have carbon recycling, technology innovation, integration of technologies, reduced fossil carbon extraction, that means longer term reserve usability, and then a more sustainable use of fossil carbon, which is very, very important for us. The CO2 conversion options are many and different, as I've shown at the beginning. We can make fuels, we can make chemicals, we can make materials. The last two we can do today using fossil carbon energy. Fuels are for tomorrow. But if you compare the market of chemicals and materials with that of fuels, you see that the latter one is at least 15 times that of chemicals. So it means that if you want to go to a large scale CO2 utilization, you must go to target fuels. But for fuels, we need hydrogen, and we need not carbon-based energy. CCU can be used for storing perennial energies, solar energy, wind energy into chemical bonds. This is very important. You can store liquid fuels. You cannot store electricity in the same efficient way. So that CCU can really have a very important role in our future. This is a representation of what Europe needs. You can make the same for all countries of the world, for India too. So the red part is what we can do today. The green part is what we have to develop for the future. And the lower part is much more important than the upper part, because it's the energy sector that we targeted. The valorization of CO2 can be also internal to a production sector. This is an example of the steel industry. You can catch CO2 emitted from the steel industry. You can use it for many different ways. For example, you can react the CO2 with the basic sludges which are produced in the steel industry and fix this CO2 into carbonates, which can be used for building roads and so. This is a permanent storage of carbon dioxide. But you can also use perennial energy, solar energy, wind energy, and convert CO2 into methanol, into chemicals, and then you go external to the sector. You move from the steel sector to the chemical sector, and you have a benefit for two sectors with an effective reduction of CO2 emission. The conditions are listed here. We need cheap perennial energy available, because this is what we have to use. If you read papers on photovoltaics, the forecast for 2040 is that they will be able to install a power of 3,000 gigawatt. Today is around 200. And the cost of energy will be very, very, very low. So that will be the point when the carbon dioxide utilization will really explode. And we must be ready for them, preparing catalysts, preparing processes in order to be able to take this opportunity. Another point is the exploitation of the aquatic biomass, which is the fast-fixing natural system, but I leave this to Angela Di Benedetto, who will speak about that tomorrow. So just getting to the conclusion, our energy system is very important. It's a key point, really. Must be accepted and supported by society, must be sustainable, must be technically reliable and economically accessible. So when we speak in terms of sustainability, and we speak in terms of closed material loops, then CO2 utilization comes in. Then you want to close the loop and continue to recycle carbon and convert carbon dioxide into useful chemicals. So getting to the conclusion, there is a great interest in making sustainable the use of coal and all other fossil fuels, but coal is the largest energy reserve, so that's very important. The integration with CO2 recovery and CO2 conversion represents a very important step for our future, and very important target for the future. And if we make a full integration of all options we have for energy production, yes, okay, sorry about that. Okay, keep silent. If we make a full integration of all the primary sources of energy we have at hand, then we shall really improve our situation and get the best out of our potential. Thank you very much for your attention.